The problem statement from GATE Physics 2014 reads as follows. Consider the process mu plus and mu minus collide to give a pi plus and pi minus. These are muons on your left and pions on your right. The minimum kinetic energy of the muons in the center of mass frame required to produce the pion pairs at rest is dash mega electron volts, and we have been given the rest mass of a muon and a pion. This is a numerical answer type question, and we have to find our answer and fill in the blank over here. Before we try to approach any problem involving relativistic kinematics, it's a good practice to go through the following pre-checks. First, you talk about what are the frames that are being talked about here. So you can see that this process is taking in a frame, so we can call it the lab frame or the rest frame. So this is usually at rest, so we need not worry about it, so it is inertial. Accordingly, there are no other frames that are being talked about except for the center of mass frame. So otherwise there are no moving frames. So this question does not arise in this problem. And number of dimensions, since the question is silent about this x direction, y direction, we'll assume it's a one-dimensional process, and only the x direction is the one which we are interested in. So it's a one-dimensional problem, and we'll take it to be the x direction. Okay. So before we solve this problem, we should go through a quick overview of the particle physics. So you can see on the left of your screen, you can see various quarks, and so up, down, charm, and so on. These are the symbols and the corresponding anti-quarks. So for instance, up quark has a charge plus 2 by 3 and a baryon number of 1 by 3, has strangeness of 0. You can see this complete table here. The pion, which is denoted by the rest mass m pi over here, is made up of up quark and a down anti-quark. So you can see that. So up quark is plus 2 by 3 and down anti-quark is plus 1 by 3. So total charge would be plus 2 by 3 plus 1 by 3, that would be 1. Similarly, baryon number is 0 for up and down both. So 0 plus 0 will be 0. And L is the lepton number, which you'll see in the next slide. And strangeness, you can see of up quark strangeness is 0 and d bar is also 0. So naturally pion will have a strangeness of 0. The other part the question talks about was the muon. It's a lepton. It's not listed here. These only the hadrons are made up of quarks. So the rest mass is mu and charge is minus 1. We'll see again. This we'll see in the next slide, the properties of a muon. So in this slide, the top 6 are what are called leptons. So for instance, we have electron, neutrino. The lepton number Le is 1. Similarly, muon and neutrino, the lepton number denoted by L mu is 1, and you can see that Le and L tau is 0 for these. And they are not baryons, so baryon number is 0 and strangeness is also 0. Similarly, this pion and kaons are what are called the mesons. So you see that their baryon number is also 0, and naturally the lepton number, all the 3 lepton numbers are 0. Proton and neutron are what are called the baryons, so their baryon number is 1. They are not strange, so strangeness number is 0, and accordingly also the lepton number Le, L mu and L tau is 0 for these 2 baryons as well. Now there is something called the conservation laws in particle physics, just like we know in Newtonian mechanics. There are some conservation laws here also. So first is that in any interaction, strangeness numbers on the left and the right should remain conserved. Baryon number must also remain conserved. So will the lepton number L tau, L mu and Le. To summarize, all these 5 numbers must remain conserved independently. They have to remain conserved independently. Now let's try to apply this understanding in this problem. So before collision, we were given 2 muons, so mu plus and mu minus. This is just denoting that on the charge on them, or you can say the antiparticle, right? So what we have over here is muon, you can say is plus 1, mu plus, so Q is plus 1. We have seen that. So and the lepton number here would be minus 1. So actually this is the particle and this is the antiparticle, hence the lepton number Le. So note that this first term is Le, second term is L tau, and the middle term is L mu. That's the notation that I am following. After collision, what happens is that it generates 2 pions, pi plus and pi minus, right? So and they are at rest. It's given in the problem. So this is the thing. First, we must say that Q must remain conserved. So Q on the right side is plus 1, and then minus 1. This should remain equal to plus 1 plus minus 1. So you can see 0 equal to 0, so charge has remained conserved. Similarly, strangeness, it's 0 plus 0, the strangeness is 0 plus 0, so again it's conserved, so this is correct. First point is also correct. B must remain conserved, so B is 0 here. Again B is 0 is equal to 0 plus 0, so B has also remained conserved. Finally Li means Le, L mu, L tau must remain conserved, so you can see Le 0 0, same 0 0 on this side, so Le remains conserved. Let's talk about L mu. So L mu, so this I'm writing for L mu, so minus 1 plus 1 is equal to 0 plus 0. So similarly L tau, you can see 0 plus 0 equal to 0 plus 0. So all the three L have remained conserved, so has the baryon number and the strangeness. So conservation laws are followed. This means this interaction can occur, right? So if this interaction is occurring, let's now apply the conservation of momentum to determine the velocities that we are, or the kinetic energies that we are required to find. So conservation of momentum, we know these are the expressions that we can use. So I'll simply write the conservation. So u1 is there, so I can write gamma 1 mu u1, this is the momentum for this particle, plus gamma 2 mu u2, this is in the negative direction based on the convention that I'm following. This is equal to 0 plus 0 because there's no, these both of them are at rest. So what I'll get is mu is common, that gets cancelled. I get gamma 1 u1 equal to gamma 2 u2, and note that gamma is nothing but u square over c square. So if you see this, I'll write it over here. So it's coming out to be u1 over 1 minus u square over c square equal to u2 over 1 minus u2 square over c square. This will be satisfied only in two conditions, rather only in one condition, when u1 is equal to u2. Their magnitudes, I'm talking about their magnitudes, direction is already in the reverse direction, hence this minus sign. So their magnitudes have to be equal, right? Then only this condition is satisfied. So let's assume that u1 equal to u2 equal to u. Okay, so we saw in the last slide that the velocity we had taken, both the magnitude was u. So now what we'll try to do is we'll try to apply the conservation of energy, the principle of conservation of energy over here, right? So on the left we have the muons. So we can write that the total energy would be kinetic energy of muons plus rest energy of muons. This should be equal to the rest energy of pions, because there is no kinetic energy of pions. Pions are at rest. So we can say kinetic energy of muons plus the rest energy. Rest energy would be, so it would be m mu c square. Again, because there are two of them, m mu c square. This will be equal to m pi c square plus m pi c square. So kinetic energy of muon system will come out to be, so it will be 2c square m pi minus m mu. Okay, so kinetic energy of muon system has come out to be twice of c square m pi minus m mu. We'll put in the values. So 1 over c square gets cancelled, it will be twice of 140 minus 105. This will come out to be 70 giga electron volts. Sorry, not giga electron volts, it will be 70 mega electron volts. 70 mega electron volts is the total energy of the original pair, this pair. So one of them will have an energy of 35 mega electron volts, and that is what we were required to find. Thank you for listening.